just in case. So somebody asked the last week about the naming. I had named a compound. I think I already changed it. Uh, where is it at? Did I change it? Was it this one? So I already went back and had changed the slides from last week. I think it was this one. I had gone this way around the circle because chlorine was higher alphabetically than propyl. And somebody said, well, wouldn't you want to go with lower numbers? And so I did some research on this. And lo and behold, the book isn't exactly clear on this. That's for one thing. But it looks like for most, I found websites that would say one way and websites that would say the other. And so here's a chemical. Don't worry about this chemical. It's nothing we're studying, but it illustrates the point. I found where it said the IUPAC name is 4,5-dichloryl-2 nitroaniline. So that would be giving the lowest numbers of 4, 5, and 2. But then it says a synonym for this is 3,4-dichloryl-6 nitroaniline, which is the way I was naming them. I was going for the chlorine first before the nitro here. But they're saying that the main name is the other way. So I think possibly what happened is there used to be a convention to going alphabetically, and they probably changed that sometime in the last 30 years. And they're saying go for the smallest numbers. And so I enhance this slide of the naming rules to say that on rings, select numbers that will be the lowest. But then sometimes it could be lowest either way. Okay, Aaron, cool. So if there's two numbering options exist with the same numbers, then you do go alphabetical. And so I have an example here of here, this could be, let's see, this has to be number 1. So you could go 2, 3, 4, 5, which is the way we're numbering it. That might not be my example. Where's my example? Oh, here it is. So in this example, we have a chlorine here, and a methyl group here, but they're in opposite sides. So you could really number this either way. This could go 1, 2, 3, 4, 5, or you could go 1, 2, 3, 4, 5. They're both 3 and 5. So in that case, you do go alphabetical, and therefore the chlorine would take precedence, and you would count this way. Does that make sense? So if you do run into the situation where you can go either way, then you do look at it alphabetically. But it appears the rule has changed so that you do it to get the lowest numbers regardless of alphabet. So like this one here is the one that I had up last week. And this would be 2 propyl, 3, 5. Did I number this wrong again? I sure did. I put a 2 here. That is wrong. Man, I still made it messed up. 2, 3, 4, 5. So this should be 4,5-dichloryl-2 propylbenzaldehyde. I'll fix that. And looks like I put another example in here. I don't remember why. So if we start here, we could go 2, 3, 4, 5, 6. But that gives us 3, 5, 6. But if I go this way, it gives us 2, 3, 4, 5. So you go this way, even though that methyl is of higher in the alphabet than the chloro. Does that make sense? So I just wanted to go over that with people before, so everybody kind of had that set in your mind. I appreciate you asking the question because it helped us clear something up with that. And I did go in the test and make sure that any questions I asked were matching this naming convention. So this slide deck for chapter 4 is updated and it's there. So if there's no question, so first question was, you can have an aldehyde where a ring member carbon is double bonded to the oxygen. And the answer to that is indeed false, because you have to have a double bond O and a hydrogen to that carbon. And if it's in a ring, you'd end up with 5 bonds to it. So that's why that is false.
On my computer.
What's that?
Sorry.
Oh, okay. Second question, name that compound. Most of you got it right. It is, you've got, your number 1 is always going to be on this aldehyde group. And it's a benzene ring, so it's a benzaldehyde. And then we're going to go 1, 2, 3, 4, 5. So 3-chloro-5-methyl-benzaldehyde. Stop me if anybody has questions. Name this compound. Question number 3. Most of you got it right. It's a dial because you've got a aldehyde group on this end and an aldehyde group on that end. And then you can number from either direction. So you're going to number closest to get you the lowest number. So that gives you 2-chloro-pentane dial. Remember, the di is for the 2 aldehydes. This one here, these ketones are isomers. This was a trick question. I apologize for this. I almost changed it, but I thought, what the heck? Anybody know what the trick is?
They're not ketones.
They're not
aldehydes.
ketones, yeah. So take that as a freebie if you got it wrong, but something just to pay attention to. I try not to do this on test to trick you, but no promises. These are isomers. Most of you got it correct. Yes, these are. I think this is right out of the lecture, if I remember right. 2-butanone and 2-methylpropanol have the exact same molecular formula, even though one is an aldehyde and the other one is a ketone.
I got a quick question for you on that question that we just had before. Like, why is it an aldehyde at the second one, the 2-methylpropanol? Because, like, how do you know that there's a hydrogen attached?
Well, you got a carbon right there, right? And it's got to have 4 bonds.
Oh, okay, yeah. Fair.
Most of you got this one correctly. What are the abbreviations for? This is an alcohol, this is an ether, this is an aldehyde, and this is a ketone. So just trying to reinforce remembering these general formulas. What is the name of this compound? Looks like about half got it correct. Is this question 7? Yeah, this is the one that most people had trouble with.
I think there might be something slightly wrong with that because there's no place to designate where the the ketone is.
Yeah, I was thinking that while I was watching you guys do this, you could have another designation in here that would be chloral dash what 1, 2, 3, 4, 5 known unknown, right? That's what you mean?
Yeah.
Yeah. So yeah, I'll have to fix that. But again, you've got this guy here is in the middle. It's on the 5th carbon, no matter which side you start at. So again, you want to go with lowest numbers, and so you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So this would be 1, 2, 3, 4 bromo, 5, 6, 7 chloro, and 1, 2, 3, 4, 5, 6. Actually, I think I got this one wrong, don't I? It should be 6 bromo, 3 chloro. So 4 of you got it right. Actually, I've got this slide wrong.
Wait, why would it be 6 bromo, 3 chloro?
I
Because
thought those naming
6.
conventions were for rings.
Well, I think that they apply to chains as well, right? Or no? I guess I'll have to go back and look at my notes again. What did we say in the notes here? What was that? Was it ketone? Where are ketones? Isomerism. Oh, I'm on the wrong chapter. Sorry, guys. I'm kind of tired tonight. My brain's not working too good. Yeah, cyclic ketones have the carbon and the other determine the name. So I didn't really specify here. I think you're going to want to start on the end that's closest to your ketone. Oops. And so what do we have here? It's the same either way. So then you would go with lowest numbers. And here I have a 3 and a 6, but here I have a 4 and a 7. So I think that's why I got this wrong. I think it should go with the lower number, not alphabetically. Those are diones. Those are isomers. I'll double check that one too, but I'm pretty sure it applies to non-rings as well. You want the lowest numbers if you can. So I'll check that while you guys are working on one of the problems. I think most people got this one right. This is 1 bromo, 1 chlorocyclobutane. Yeah, this is not on the 2nd carbon, so they're both on the same carbon. So it's not 1, 2. And then here you want to list them alphabetically. So that's why it's 1 bromo, 1 chloro. What kind of isomers are these? Most of you got it correctly. It's positional because the ketone group is just on a different carbon in the chain. The chain itself hasn't changed structure. So this is a positional isomer. What kind of compound is this? Remember, aldehydes take higher priority over ketones. So that's why this is an aldehyde. So you have to go back and look at that chart of priorities again. What kind of compound is this? Most of you got it correct. It is an alcohol because that alcohol takes priority over the alkene. And so this is an enol. If you oxidize a primary alcohol, what do you get? Most of you got it right. It's an aldehyde. And this one here, what is this? It is a hemiacetal because we've got this ROROH. This makes a hemiacetal. If it was an acetal, this would be an R as well. And an ether is ROR. There's no O, no OH in it. And then last question, if you react a ketone with an alcohol, what do you get? It looks like most of you got it right. You're going to get a hemiacetal, adding an alcohol onto a ketone. So you can go back and look at the slides from last week and see those. Okay, any questions there? If not, we will move into chapter 5. What time is it? Let's see here, 6:34, okay. So we're good. Start my slideshow. So tonight we're going to talk about carboxylic acids, esters, and a few other minor creatures. Let me get my pointer thing back. There we go. So first of all, we're going to talk about carboxylic acids. Oh, before I get into this, so exam 2 is this weekend. It will kick off on noon Friday. You have until midnight Sunday night, just like normal. It's only over chapters 3 and 4. And an announcement will go out when it kicks off and all that. So any questions about that at all? Okay, carboxylic acids. A carboxyl group is a C double bond O OH. So the general formula for carboxylic acid is RCOOH is how it's usually drawn shorthand. Some examples here. We've got 3 carbons with this carboxyl group on the end. It can be in a ring structure like this, with here's your carboxyl group off the side. There's also a methyl group here. And it can even be a benzene ring. Remember, this is my shorthand for benzene. So this is a benzene ring with a carboxyl group on the side. Naming rules. So select the longest chain with the carboxyl group if it's a chain. You name the parent chain, adding the ending oic acid. You number the chain starting with the carbon in the carboxyl group, or the closest end to it, I guess. Locate and name your other functional groups. If it's attached to a ring, always count the carboxyl carbon as number 1 and number the rest to give lowest location numbers. The ring is given the name, your number of carbons, so like pentane or butane, carboxylic acid. We'll see some examples of this. If it's a benzene ring, however, then it gets the name benzoic acid. The funny thing is the book tells you, this is a change between editions 4 and 7. In edition 7, it tells you that benzene carboxylic acid is the proper name for it. But then I went back and looked at the problems at the end of the chapter, and they gave all their answers as benzoic acid. So even though this is sort of the current fad for how to name these things, or it's the current rule, still people use benzoic acid all the time, including the book. But in case they didn't always do that in the book, I wanted you to be aware of this. Our purposes, it'll be benzoic acid. So here's some examples. Here we have 5 carbons and then an additional carbon outside of the chain. So we're going to start numbering on this end with this carboxylic acid carbon and go this way. So this will be 4-methylpentanoic acid. So this is that 4th methyl one on that 4th carbon there. And it's pentanoic because there's 5 carbons in the chain, in the main chain. In a ring like this, it's a 5-carbon ring. So this is going to be number 1. So this just becomes 2. And it's a methyl group. So this is 2-methyl cyclopentane carboxylic acid. So the cyclopentane is this ring, and then carboxylic acid to denote that it has this carboxyl group on the side. Any questions there on either one of these? Here's a benzoic acid. So this is a benzene ring. We're going to start the numbering on the carboxylic carbon right here. And then now we start numbering around. I believe in this case it doesn't matter which way you go because they're both chlorines and they're both in the 3 and 5 positions. So you get 3,5-dichlorobenzoic acid. Any questions there? And you can have dicarboxylic acids. So we've got a carboxyl group on this end and a carboxyl group on this end. So and we've got 1, 2, 3, 4 carbons. So this becomes butane dioic acid. Again, the di is indicating that you've got the 2 carboxylic acid groups. And then this methyl group here is on the 2nd carbon. So that's 2-methyl butane dioic acid. Any questions there?
Could you, oh, sorry,
ahead.
could you quickly number that?
So you've got 1, 2, 3, 4. Or you could count it this way, 1, 2, 3, 4, right? But this would give you 3, 1, 2, 3. This would give you 3-methyl. This gives you 2-methyl. So this would be the one to choose because it gives you the smaller number. Does that make sense?
Thank you.
There are some common names. So the smallest carboxylic acid that you have is just a carbon with a hydrogen on it. And this is called formic acid. And the reason why is that this acid was distilled from ants originally. This is when ants bite you, or at least some kind of ants. I don't know if they all do. And you get that kind of sting. It's because their bodies naturally generate this acid, and we would call this methanoic acid, but it has the common name formic acid. That's what it was originally called. Acetic acid is with a CH3 onto a carboxyl group. And this is the common name. You guys have probably worked with acetic acid in the lab. It's a mild acid. We would call it ethanoic acid because there's 2 carbons here. Acetum is the Latin name for sour, and that's where acetic acid comes from. And then here we have 1, 2, 3, 4 carbons. So we would call this butanoic acid, but another common name for this is butyric acid. And the reason why, again, comes from the Latin butyrum, means butter. And this acid is generated when butter goes rancid. This is what gives the rancid taste of butter, is butanoic acid. So here's one to practice. Give me the name of this compound. Just go ahead and type it in. When you're ready, we'll give you a few minutes. Okay, we got one opinion in. Got another couple in. Alrighty, let's see here. Yep. So you've got 1, 2, 3, 4 carbons in the main chain. Remember, this is a carbon here that's got that double bond OOH. So that's going to be butanoic acid, and then we start numbering here. So that's 1, this is 2 ethyl, 3 bromo. Good. All right, you can have unsaturated acids. So this is where you have a double bond in there, but there is a carboxylic acid group. And so this gets changed from oic acid to eoic or eoic acid. And then you indicate the location of the double bond. So here we've got 1, 2, 3, 4, 5, 6 in the main chain. And we got a methyl group hanging off here. So we start numbering here again, 1, 2, 3. So that's 3 methyl. And then the first carbon in the double bond is the second one. So that's 2. And then because we've got 6, it becomes hexanoic acid. By the way, this is the primary ingredient in body odor. It's formed by skin bacteria in your armpits. Fun fact, you can drop at parties or something. Impress your friends. Any questions there with this one?
Does that have a common name other than BO?
I don't know offhand. You could go, man, you're really reeking a 3-methyl-2-hexanoic acid. And they'll be like, what? There could be. All right, when you have unsaturated carboxylic acids, then you have the opportunity for isomers and so stereoisomers. So you can have cis and trans configurations here. So here we've got 5 carbons, 1, 2, 3, 4, 5, but there's a double bond in here. If we draw our imaginary line through here, you can see that these 2 carbons over here are on opposite sides of the double bonds of this carboxyl group. And so this would be trans 2 pentanoic acid. Pentan because it's 5 carbons and you got a double bond in there. And the 2 is denoting that it's on this second carbon here. And here is a cis. You still have 5. It's still pentanoic acid. 1, 2, 3, 4, 5. But now if you draw your imaginary line, you've got these guys on the same side of that double bond as your carboxylic group. And so this is a cis-2 pentanoic acid. Any questions there? You can also have what are called hydroxy acids. These are carboxylic acids that have an OH group in them as well. And so the hydroxy just becomes the functional group name. So here we've got 1, 2, 3 carbons. So this is propanoic acid. And then this is the first carbon. So this is the second one. So it's 2-hydroxy propanoic acid. This is also commonly known as lactic acid, which exists in sour milk, sauerkraut, dill pickles, and in your muscles. If you go to the gym and work out, like I did yesterday, I did cardio boxing with my virtual reality headset, and my muscles hurt today. That's because when you're using your muscles, you get a side effect of lactic acid building up in those muscles. And so that's the source of your soreness in your muscles. So that's 2-hydroxypropanoic acid. Here we've got a dicarboxylic acid with 2 hydroxy groups. This is 1, 2, 3, 4. So it's going to be butane dioic acid. And then your hydroxys are on the second and third carbon. So this is 2, 3 dihydroxy butane dioic acid. This is commonly referred to as tartaric acid, which is the taste you get from overly ripe grapes. Or I guess just ripe grapes. Don't have to be overly ripe. This is citric acid. So you've got, again, 3 carboxylic groups on here. So it's called a tricarboxylic acid. And you've got the 3 carbons in here. And you've got the 2, or the hydroxy group on the second carbon. So this becomes 2-hydroxy propane, And then 1, 2, 3 tricarboxylic acid.
I'm reading that as a pentane.
Yeah, this is named a little differently. You're right that there's 5 carbons in there, but because of this 3 groups, it gets named this way. And then we can also have what are called keto acids. This is a carboxyl group, takes priority over this double bond oxygen here. So this is butanoic acid, and this is on the second carbon, so this gets called 2-oxobutanoic acid. These are known as keto acids because you've got this ketone group here. Any questions there? And you can also have amino acids. These will become very much, amino acids are one of the building blocks in the human body and probably animal bodies as well, I would presume. So again, the carboxyl group has priority. The amino group gets the name amino. This is just an ammonia NH2. And so again, you've got 4 carbons up here, 1, 2, 3, 4. So it's butanoic acid, and then it's on the second carbon. So this is 2-amino butanoic acid. How are we doing on time? So let's do the practice and then we'll take a break. So try to name this bad boy. Okay, got a few answers coming in. All right, looks like we have a general consensus. Yes, 2-propanoic acid, because you got the double bond here. So we've got 1, 2, 3 carbons. And the single bond, the double bond is going to be, you always start number 1 here. So the first carbon in the double bond is on the second carbon. So that's 2-propanoic acid. Good. Draw 4-chloral 3-oxopentanoic acid. Again, just draw it and tell me when you're done. We'll look at it. All right, Kayla's done. How the rest of you doing? Okay, sorry you're not feeling well, Laura. We'll see you. All right, you guys done? So did you get something like this? So here we have our carboxyl group. So this is going to be the first carbon, second, third, fourth, fifth. So that means this is 3-oxo, and this will be 4-chloro. Good.
Wait, what's the 3-oxo?
This is the third carbon here that's got that oxo group on it. So this is your carboxylic group here. You always start numbering with that first carbon. So that would be 1, 2, 3-oxo, 4-chloro pentanoic acid.
Do you not like start with like the first like double bond to the oxygen? Like you don't like why do you count like 3 and not count that like as one like in the name?
Don't count in the name. So you got 1, 2, 3, 4, 5. So that's a pentane,
Yeah.
right? So that's pentanoic acid. Then on the third carbon, we have this oxo group. So that's 3-oxo. And the fourth carbon here has the chlorine. So that's 4-chloro.
Like why isn't it like 1,3-oxo? Why is it just 3?
The other double bonded oxygen is part of the carboxylic or the carboxylic acid group.
Oh, you're
Oh,
thinking
so
of
It
this
doesn't
one
look
here?
like it because his OH is super long, so it kind of looks like an extra carbon on there, but it's not.
Oh, sorry. Yeah. Yeah, you have to remember there's not a carbon here. This is a carbon right here, and it's got the double bond O and then an OH group. So there's only one carbon here, but this whole thing is the carboxyl group. It includes the carbon. So you're not going to name this because that's part of the oic acid part. Does that make sense?
Oh yeah, got it.
Okay, well, we're probably at a place to take a break. Yep. So let's take a break. Let's be back at 7:15. And I'm going to pause sharing and pause recording. I'm actually digging this recording without, if I record Zoom through Zoom, which is what I did last semester the whole time, it takes a long time to process the video. I'm using this other program to do it, and it's done within like 2 minutes of us ending class. So I just upload it to YouTube, go to bed, and it's up there within 20 minutes or so. So it's pretty cool. Anyway, physical and chemical properties of carboxylic acids. Boiling and melting points. So both the carbonyl group, the C double bond O, and the hydroxyl group in our carboxylic acids are very polar because of these oxygens, and therefore they have very high melting points and boiling points. Carboxylic acids can form hydrogen bonds with other carboxylic acids. These are called dimers, and this also contributes to the higher boiling point. Solubility. Smaller chain carboxylic acids are water soluble, because they form hydrogen bonds with the water molecules. And they're also polar, so that polarity is going to help dissolve in the polar water as well. In general, aromatic carboxylic acids are not water soluble. So if there's a benzene ring involved, they're generally not water soluble. Chemical reactions with carboxylic acids. So if you downloaded these slides before yesterday, you might have different slides. I was working on this yesterday, and I found some slides that I liked. I found some images that I liked better. I think it explained it more. So you may have to download the new ones if you already did. So a primary alcohol can be oxidized into a carboxylic acid, and this happens in 2 stages. Here's your primary alcohol. So right here's your carbon with the OH, and it's got 2 other hydrogens on it. You can oxidize that into an aldehyde, and what happens is you lose the hydrogen off of this oxygen, and you form the double bond there. And so you end up with a COH, which is an aldehyde. But then it can be oxidized even further into a carboxylic acid. And so what happens here is you lose this hydrogen, and then an oxygen hydrogen bonds in to that place. And and you know it's that way because this hydrogen is bonded to the carbon here. But here, this hydrogen's bonded to the oxygen. The oxygen's bonded to the carbon. So you're popping this hydrogen off and then bringing an OH group and adding it in to make the carboxylic acid. So you go from a primary alcohol to an aldehyde to a carboxylic acid. Any questions there at all? This can also happen with aromatics. So here we've got a benzene ring. It's got a carbon, 2 hydrogens, and a chain, an R chain. This oxygen is going to come in and replace this. This R group is going to break off. This hydrogen is going to break off. This oxygen comes in and replaces that. And then you also get this oxygen coming in and replacing this hydrogen. And so you get your carboxyl group onto the aromatic ring. So it's happening on this constituent hanging off of the ring. And it doesn't matter how big this R group is, it's gonna get lopped off. So here we've got this carbon right here, and then it's attached to another carbon. That carbon's gonna get removed, and it will form the C double bond O OH. But if you had one with a propyl group attached to it, the same thing, that R group gets cleaved off and it gets oxidized into the same thing. So it doesn't, remember R just means any length of a carbon chain. So it doesn't matter. This could be like really, really long. It doesn't matter. It gets clopped off and you get your carboxylic acid formed. Any questions there at all?
With the like 2-step process and things like that, are we always gonna know like, oh, this is like oxidization 2 steps, or is it gonna just be like oxidization and we are to assume that it is like completely oxidized?
Well, first of all, let me make sure you're not misunderstanding this as a 2-step, right? This is 2 compounds oxidizing into the same one. Do you get that?
Yes. No,
Okay.
I'm so sorry.
All
I
right.
meant to ask this question like a
Yeah, that's fine. I just wanted to make sure because I was worried this might confuse people. But yeah, you're exactly right. What you might get is a question that says, if you mildly oxidize a primary alcohol, what do you get? And that answer would be an aldehyde. But if it says you like fully oxidized a primary alcohol, or something, or strongly oxidized a primary alcohol, then your answer would be a carboxylic acid. Does that make sense?
Yes, thank you.
But I just want to make sure people weren't thinking this was these are two different reactions. It's just showing you. And all of your R substituents can be oxidized. So here we have a methyl group hanging off of this benzene ring, and here we have an ethyl group coming off of that benzene ring. This will get lopped off, and you'll form a C double bond OH, and this just loses its hydrogens and becomes a C double bond OH. Remember, this is a CH3 out here, right? So it loses its hydrogens, and so you'll get a dicarboxylic acid here with a benzene ring in this reaction. So it will attack all of these chains that are hanging off of the benzene ring. This can happen with fused rings as well. So here we have a benzene ring, and then it's got a cyclopentane fused onto it. And again, you've got a carbon here and a carbon here that's got hydrogens. So it will break off this R. In this case, the R just happens to be the rest of the ring. And then you'll get your benzene ring with two carboxylic acid groups hanging off of it. Does everybody see that? So it's breaking this off and breaking this off as the R that gets thrown away. And then you're going to oxidize this carbon and oxidize that carbon. All right. You can also form carboxylic acid salts. This becomes important in biochemistry as well. Carboxylic acids will react with strong bases to form carboxylic acid salts. So here we have a carboxylic acid. It's got the C double bond OOH here. And sodium hydroxide is a very strong base. You actually don't want concentrated forms of that to get on your skin. It will burn really bad. And this will form what is called, what happens here is that this hydrogen gets kicked off and the sodium gets added to this, but it's an ionic bond. We end up with what's called a carboxylate ion. It's going to have a negative charge because you've lost the positive hydrogen. This positive hydrogen is going to join with the OH to give you water. So that's your H2O. And then now you've got a positive sodium that has an ionic bond with this carboxylate ion. And these carboxylic acid salts we will see play a role in body chemistry. Any questions there? Cool. And then you can reverse this reaction. You could convert a carboxylic acid salt back to a carboxylic acid with a strong acid. So here is our carboxylic acid salt that we were just looking at. And then use a strong acid like hydrogen chloride, and you will reverse that reaction and you will get sodium chloride. So this chlorine will pull that sodium away, and then this hydrogen will go on to that oxygen and reverse this reaction. Any questions there? All right, some real world uses of carboxylic acids. Fun, fun. Pain relief, naproxen. It's the active ingredient in Aleve for joint pain. Naproxen is particularly good at joint pain. I am blessed with inheriting the propensity to gout from my parents. God bless their souls. And if you've never had gout, let me tell you, it's very painful. Naproxen is great for gout because that's a joint. Gout is a buildup of uric acid salts in your joints. And so this is naproxen. You've got two benzene rings fused together. You've got this OR group on this end, and then here's your carboxylic acid group. And naproxen's a wonderful, wonderful little drug. Skincare, hydroxy acids. Remember we talked about this. You got a carboxylic acid, but then an OH group. These are hydroxycarboxylic acids. They are used because they accelerate the flaking off of dead skin, making healthier looking skin. So these are quite often used in lotions and creams and things for your skin. And we had already looked at this one earlier. 2-hydroxypropanoic acid is also called lactic acid. This is quite often used in skincare products. Common chemical used for acne are polysaturated carboxylic acids, and they dissolve into the oils on your skin, preventing the bacteria and the dead skin cells from sticking, and therefore not causing the acne. A very common one is, I don't even know how to pronounce this, tretinoin or noin. But you can see here we've got a ring, an alkene ring with a whole bunch of double bonds in here. And then here is your carboxyl group on the end. And this is a common ingredient used in treating acne. If you look on the back of your of an acne medication, this is quite often what you see there in the list of active ingredients. Foods, salts are used in food preservation. Sorbate salts inhibit yeast and molds in dairy, dried fruits, and some meat and fish. And so here you can see we've got double bonds in here. And then this is a carboxylic acid salt because the hydrogen's gone. And you've got a negative here, negative charge. And we've got a potassium ion. These are called sorbate salts. And what these do is they will react with the yeast and molds instead of the food reacting with them. So this causes your food to last longer if it's added in. A benzoate salt is where you've got a benzene ring with the carboxylic acid salt group on it. So again, here we have this O minus because the hydrogens come off. This is called a benzoate. And with the sodium, these inhibit yeast and molds in beverages, jams, and syrups quite often. And then here, propionate salts. So you've got 3 carbons with an oxygen with a minus sign. In this example, there's 2 of these. You see the parentheses around here with a calcium ion. And these inhibit yeast and molds in baked goods and cheeses. So again, I'm not going to ask you to name these compounds. I'm not going to ask you to memorize these. I might ask you, do carboxylic acid salts, help preserve food or something like that. So that's the primary thing. All right, and that's it for carboxylic acids. Any other questions or comments before we move on? How are we doing for time? 7:34. All right, we'll keep rolling. Okay, esters. So our carboxylic acid was RC double bond OOH. So an ester is an OR. And again, the shorthand version of this is just RCOOR. So often gets used to designate an ester. So it's just having another carbon chain here instead of a hydrogen. How esters are formed is they're usually formed with a carboxylic acid reacting with an alcohol. So you see here we have this carboxylic acid group. Here we have this OH alcohol group. And then you form the ester by taking the R from the alcohol, and it replaces the hydrogen here. And this hydrogen joins with the OH to give you water. And so now you have an acid side of the ester. That's this blue box. And you have the alcohol part. That's this R prime that came from this alcohol here. So all esters have an acid part and an alcohol part. This becomes important in naming them. Any questions there? Okay, naming rules. So like we just said, esters have an alcohol part and an acid part. You name the alcohol part first, but you use its alkyl form. And then you name the acid part second as a separate word, dropping ic acid and adding ate. So here we've got this ester. The alcohol part is this CH3. That's that R that came in and replaced the hydrogen. This whole part here is your acid part. So you take this and you call it methyl. That's the alkyl form of that. And then this, you've got two carbons here. So this is ethanoate. Instead of ethanoic acid, it's, the ethanoic acid would have been the carboxylic acid form of this, right? That's right here. Oops. So this would be ethanoic acid, and this would have been methanol with just a CH3 here. And so now you get methyl ethanoic acid. I'm sorry, ethanoate. In this case, we had CCCOH as our alcohol part. So that gets named propyl. And then this is a benzene ring, so this becomes benzoate. This is your acid part over here. Any questions there with that? Clear as mud. Silent group tonight. So here's some examples. On our alcohol part, we've got an ethyl group. So this was ethanol, and it came in and reacted with this. So that's ethyl now. And then we've got 1, 2, 3 carbons. So that's propanoate. And over here, we've got an ethyl group. So that's the same as this. I just drew it not in a stick formation. So this was an ethanol originally that bonded in here. So that's your ethyl. And then here you've got a propyl, but you got a methyl group hanging off of that. So this becomes 2-methyl propanoate. So ethyl 2-methyl propanoate. Any questions there? You can have diesters as well. So we have an ROCOOR on this end, and we have an RCOOR on this end. So how this gets named is we look at our alcohols. In this particular case, it's a methyl and a methyl. So this gets called dimethyl. And then we've got 1, 2, 3, 4. So that's butane dioate to denote that we've got one of these on either side. So dimethyl butane dioate. This is a diester. Any questions there? All right, other functional groups, they just get named like we normally would. I think I already gave you an example of this. But here is our alcohol side, but there's a chlorine on it. So this is ethyl. So this would be 2-ethyl, because we start naming from over here where it's bonded in. So this is 2-chloroethyl. And then our 3-carbon acid side would be propanoate. And then here we've got methyl. So that's the methyl part, that's our alcohol part. But then we've got this oxo group here on this carbon. So we got 1, 2, 3, 4, that's butanoate. And it's on the 3rd carbon. So that's 3-oxobutanoate. Any questions there? What a name. Which one are you referring to, Aaron? This one here, or was it the previous one?
The previous slide.
Yeah, this one here.
dimethyl.
Oh, yeah, they can get hairy. This is why so often you end up with common names for everything, because nobody wants to lay out those long names. Okay, you can have cyclic esters. These are called lactones. So what can happen is your OH, if you have an OH group on the end of a, sorry, my brain's not functioning here. So this is a self-reaction. So this alcohol is actually coming in and bonding with this carbon. And so it's going to form a ring. And what you end up with is you've got 1, 2, 3, 4 carbons, just like you got here. But then your 5th ring member is an oxygen, not a carbon. And then you've got the double bond O on the on here. And so this has become now an ester, right? This was a carboxylic acid with a hydroxy group on it, but it's merged in and formed a ring and has become a cyclic ester. These are called olides. And so what you do is you count the number of carbons you had. And so you get 4 carbons. So it's butanolide. And 4 is telling you that this oxygen is attached to that 4th carbon over here. So this is showing you the structure of this. Is lactone related anyway to milk? Yes, I believe so, and I'm trying to remember. offhand. This comes up in body chemistry, but I can't think of it at the moment off the top of my head. But yes, it is related to lactates and lactic acid and lactose. Lactose, yeah, lactose is a sugar, the sugar that's in milk. So this is 4-butanolide. Any questions there? So,
Wouldn't it be like obvious? Like, wouldn't you? Sorry. So, like, my idea would be, would you not have to put like the 4 in there? Because wouldn't it be obvious if it's an olide? Or no?
well, this could be over here, perhaps. So it's telling you that it's on the 4th one where it's at.
Would it still be an olide if it was like on the 3rd carbon?
Yeah,
But it wouldn't be an ester then, right?
if it was in here, you still have C double bond O. Oh, yeah, I guess it wouldn't be an olide anymore. Yeah, but this is the naming convention is to designate that.
They want you to put it in. Okay, that's fine.
And then here's 5-pentanolide. So again, you're going all the way around here with your 5 carbons, and then this is in the 5th, attached to this 5th carbon. Okay, so here's an ester. So give this a whirl to name this. Oop. Keeps wanting me to reboot. Okay, 2 of you got ethyl 3-bromopropionate. Anybody else? Yeah, it says here that lactones were originally derived from lactic acid, and that's why they got the name. All right, let's see what we got here. So yes, it is ethyl because you've got 2 carbons here as your alcohol part, and then 3 bromopropionate. 1, 2, 3. So you got your bromine over here. By the way, I want to look back at this thing for a second. The reason for the 4-butanolide is because that oxygen could be here. That's still an RCOOR. So you could have a 2-butanolide and a 4-butanolide. Does that make sense?
That does. Thank you so much.
They also sometimes use Greek letters, but I didn't include that in the stuff, so you don't have to worry about that. So if this was here, this could be like called gamma butanolide, but don't worry about that. I decided not to do that stuff. Okay, how about this guy? What are you gonna call it? Yeah, Kayla, what do you think? Or is it an ISO? Michelle thinks so. Anybody else want to weigh in? Okay, Sierra agrees with Michelle. So yes, this is isopropyl propionate. You've got this 3 carbons over there. Good. All right, physical properties of esters. Esters cannot form hydrogen bonds with each other, thus they will have lower boiling points than alcohols and carboxylic acids of similar size. So there's just no hydrogen oxygen bonding that can occur within itself like that. Esters can form hydrogen bonds with water. Thus, smaller chain esters are water soluble. Small and medium mass esters are usually liquid at room temperature. Most esters have pleasant odors. A lot of esters are produced inside of fruits. Real word uses for esters. Flavoring. So like I said, a lot of fruits. Methyl butanoate. So we've got a methyl group on the end here. And then a 4-member chain. So methylbutanoate is a active ingredient in the flavor of apples. Ethyl butanoate, so just having one more carbon on there, gives you pineapple. Isn't that pretty amazing? Just one more carbon changes it from an apple flavor to a pineapple flavor. Maybe that's why they're called pineapples. They're like kind of like apples. I think that was based on its looks, not taste, but it's just kind of funny how just one extra CH3 here can make such a difference. So esters are responsible for flavors in fruits and flowers, and therefore they're often used in artificial flavoring. Esters also exist in pheromones. Pheromones quite often have ester functional groups. So here we have isopentyl ethanoate. So you've got this isopentyl right here, and then ethylnoate. This is the active ingredient in a pheromone that bees release when they want to signal alarm to the whole hive. And I always have to tell this story because we, in organic synthesis class in undergrad, we were synthesizing a compound, and a byproduct of it was this isopentyl ethanoate. And one day I was walking down the hallway in the lab building, and this kid, I wasn't in this organic lab at that time, I'd already done the lab, but I'm walking down the hallway and this kid runs by me like a bat out of hell down the hallway. So I wander into the lab and I'm like, what's going on, guys? Well, this student was highly allergic to bees stings, and unbeknownst to them, there was a beehive outside the window, and they had the window open, and it was generating this attack pheromone. And a couple bees came in and were flying around the lab, very agitated. And he didn't have his EpiPen with him, so he was getting out of there to get away from any possible bee sting he might get. And then when dogs go into heat, they generate a pheromone. It's methyl 4-hydroxybenzoate. So you've got the methyl here for your alcohol part, and then you got a benzene ring with a hydroxy group on it. So this is the 4-hydroxybenzoate. This is the active ingredient in what female dogs release when they're in heat. Another pheromone. Catnip has a ester in it. You've got your RCOOR. It's a fused ring. This is called nepentolactone. So there's your lactone part of it because it's in a ring. And this is a common name. But this is the active ingredient in catnip that makes cats all happy. Medications. Benzocaine is used as a tropical anesthetic. I'm sure you guys have probably heard of benzocaine before. And again, this is not its full legit name, but it is a ethyl group here, and it's an aminobenzene here. So this would probably be 4-aminobenzoate, and this would be ethyl, so it'd be ethyl 4-aminobenzoate. But it's commonly called benzocaine, and this is a topical anesthetic. Aspirin also has an ester in it. So we have an ROCOR here. So this is an ester. And this is also referred to as salicylic acid, or commonly known as aspirin. Both of these are painkillers. Okay, isomerism and esters. So we talked about before that you could have positional estimers sorry, it's getting late, guys. Positional isomers. This is just kind of a review. We had 1 pentene and 2 pentene. Its differences within the chain is a positional isomer. And we also had skeletal isomers, differences in the structure. So this is 1 hexene, but this is 4 methyl pentene, because this one of the carbons got pulled out and is now a functional group. And we can have skeletal isomers with carboxylic acids that we talked about. So both pentanoic acid and 2-methylbutanoic acid are isomers of each other because they have the exact same molecular formula. So carboxylic acids can have skeletal isomers of one another. Esters can have positional isomers. So both methyl propanoate, here you got 1 carbon, so that's methyl, 3 carbons propanoate, has the exact same molecular formula as ethyl ethanoate. So we're just kind of moving the double bond over. And so you've got ethyl ethylnoate. These two are isomers of one another. But it's positional because all we're doing is we're not changing the main chain. We're just changing where that double bond oxygen's at. Any questions there? You can also have isomers between esters and carboxylic acids. So here we have ethyl propanoate. So you got 2 here, that's your ethyl. 3, that's your propanoate. This has the same molecular formula as pentanoic acid. And so these two are isomers of one another. Any questions there? All right, chemical reactions. Okay, esters react with water to form carboxylic acids and alcohols. So you're basically reversing the reaction that we looked at to make an ester. So you've got RC double bond OR reacted with water in the presence of acid. You will reverse this formation and you will end up with a carboxylic acid and your alcohol again. So we saw in the beginning of this talk of going this way, it's now going back that way. So this is called a hydrolysis because you're adding water to it to form your, to cause for the reaction. Esters react with strong bases to form carboxylate salts and alcohol. And this is called saponification. And so you have your ester, RCOOR, a strong base with water, and you will get this carboxylic acid salt, and you'll get an alcohol. So this R comes off and forms ROH with this hydroxy group, and the sodium comes in and is attracted to this negative oxygen there, and you get your carboxylic acid salt. Any questions there? You can also have thioesters. Remember, thio refers to sulfur. Carboxylic acid will react with a thiol. So this is a thiol. Instead of an OH, it's an SH. You remember from one of our previous lectures. So this carboxylic acid, we got RCOOH, reacts with a thiol, and it will give you a thioester. So again, we have an alcohol group right from here, a thiol group in this case, the sulfur, and then you have your sulfur instead of an oxygen, and then so this is your acid part, and so this is a thioester, and you get water as a byproduct. And I think I got some, no, I don't have any names examples. Maybe I do. I guess not. Polyesters. I'm sure you guys have all heard of polyester. Well, this is what it is. Esters can react with one another to form polyesters. So here you can have this repeating ester unit that, so this is an RCOO, and then there'll be another R over here. And this can repeat n times to form a polymer and just build out those giant chains like we saw before. And polyesters are used in synthetic fibers. Whenever we talk about polyester, it's quite often PET, polyethylene terephthalate is the name of this, and that's used in synthetic fibers. But also in other ways too. This is a polycarbonate, and these are used in plastics such as like eyeglass lenses. So you probably heard of polycarbonate glasses, and that's what that's referring to. And you'll notice that there's benzene rings in here, and there's a benzene ring here as well. Again, I'm not going to ask you to memorize these or anything like that, but just knowing that your esters can polymerize and make long chains. Any questions there? Okay. Why don't we take another 10-minute break, and we will wrap up tonight with acid chlorides and anhydrides. So let's come back at 8:15. We'll make it a 9-minute break. And I'm going to pause recording again. This is missing now. Let's go back real quick. All right. I'm not going to go through it all again, but since I forgot to hit record again, I am sharing, right? Okay. So we have acid chlorides and anhydrides. Acid chlorides is what we react a carboxylic acid with an inorganic chloride to form an acid chloride. You name it by replacing oic acid with oil chloride. So we have 3-methyl pentanoyl chloride. Acid anhydrides is when you pull water out of 2 carboxylic acids, and then the remaining parts combine. And this is an acid anhydride. So we have RCOOCOR. And these are often used to synthesize esters. If it's symmetrical, then you just use the term ethanoic anhydride, and that tells you that it's a 2-carbon on either side. And then if they're not symmetrical, then you use the parent name from the 2 carboxylic acids. So this is ethanoic propanoic anhydride. All right, inorganic acids can react with alcohol to form esters. So again, this is a very important one in body chemistry. You have phosphoric acid. So here's a phosphorus surrounded by 3 hydroxy groups and then a double bond oxygen. This is phosphoric acid. It will react with an alcohol, and this R will replace this H here. So you get now what's called a phosphate ester, because this isn't a carbon here. So the phosphate becomes a phosphate ester. And phosphate esters are very important in body chemistry. And then you get the H reacting with the OH in the alcohol to form your H2O. Any questions there? So yes, phosphate esters are very important in biological systems. How they get measured is this is a phosphate as your core name. So you've got the phosphorus with these O's with negative signs on them because the H's have been pulled off, and then a double bond O. So here, if you have a methyl group added onto the oxygen, then this gets called methyl and then dihydrogen phosphate. So the phosphate is the P in the O's. So the dihydrogen is I got a hydrogen on this oxygen, hydrogen on this oxygen, but there's a methyl group on this oxygen. So this gets called methyl dihydrogen phosphate. If you've substituted two of the hydrogens, then this becomes dimethyl hydrogen phosphate. And if you substitute all three of them, then this would become trimethyl phosphate. Any questions there at all? Turns out that phosphorus is actually very important in body chemistry, and the phosphate in particular, as we will see. I always read your guys' chats late, so I don't know what Lydia's laughing at, but cool. I really wish that'd make a sound when somebody posts in there. Nitroglycerin, which we talked about before. It's used as an explosives, but it's also used to treat angina with your heart. This is a trinitrate ester. So you've got these nitrile groups in 3 different locations. Oh yes, if we were all burned out as you are, yeah. Yeah, I'm getting fried. So this is a trinitrate ester in nitroglycerin. Oh, that's the end. Okay, I thought I had a few more. So I have problems here for both 4th edition and 7th edition. By the way, I noticed that one of the, I don't know if I gave you this problem or not. Maybe I skipped it for that reason. Let me see. 35. No, I gave it to you. Yeah, so like in problem 35 of the 7th edition, there's one that asks about an alpha beta. And remember, we didn't cover that, so I wouldn't do that one. You can do the other ones in there, but don't worry about anything that's got Greek letters on it, since we didn't cover that. So yeah, so that's the problems.
Could you give us any other pointers to increase our grades from the last exam?
You know, I was thinking about this the other day, trying to think of what I could suggest, and I don't know what you guys are doing. One thing I would recommend, I think I mentioned one night that when I was in undergraduate organic chemistry, we had to memorize hundreds of these reactions. And I put them on 3x5 cards. So you could do that as well. You could make out a 3x5 card and maybe put this on the front and then put the answer on the back so you could look at it and say, oh, if I react two carboxylic acids together, what am I going to get? So that might be a good way to just prep when it comes to reactions. Certainly doing the problems in the back of the book is good preparation. But if you're having trouble with reactions, then the best thing to do is just kind of memorize them. I don't know, what kind of things do you guys do for preparation for test? Like you could make yourself a flashcard that says, what is this? And then on the back, you could have that it's a carboxylic acid salt, you know, things like that to try to help you prepare. Try to think of what else might recommend. You know, like you could make yourself a flashcard, say, you know, what is a positional isomer versus a skeletal isomer to help you just get that down in your head. I'm not testing you on this stuff anyway, so, you know, you don't have to worry about that, but you might, you know, could say, do esters that are used in flavoring, you know, artificial flavoring or something. I don't remember if I asked anything like that on the exam. I kind of doubt it, but never know. I don't know. Does anybody else have any? Yes, Kayla says the organic chemistry tutor on YouTube. Yeah, if you're struggling with a particular concept, it's YouTube is your friend. I think I gave you him and some others in the very first night to go back and review and look at those. The only thing you might run into is where they might be using a newer naming convention or something, or they might be using an older naming convention. So you have to kind of use some discernment, but there's a lot of good stuff out there. New one I just found, I'll put it in the chat for you guys. I think she's really good too, is it's called, oh, what is it called? Let me look it up here. I think she does really good videos. It's something like Leia for chemistry or something like that. Leia for science. It's LEAH 4 SCI. Another really good YouTube channel. That's actually where I got her. I ripped off her slides when I replaced my crappy drawings. Right here, these things here. This was all from her, one of her videos. This thing here, I thought it laid it out better than how I had mine drawn. So that's another good one to use. So again, yeah, you could make up a flashcard that would test primary alcohol to aldehyde to carboxylic acid. And if you want, I can pause sharing for a second and just scan over the test. So I'm going to have to pause.